It's David Praise Kumakalu once again. I'm glad to also mentor you on this course. So today we'll be talking about a really nice machine learning algorithm. It's very simple. I'll be going through like the intuition behind the naive Bayes algorithm. So we're gonna see some examples, how it works. We're gonna work a bit on the theory, go through a bit of it, not too much in details. And we'll also go through some Python examples to show you, how to use it, how to apply it, to see how it works and how it's able to perform classification. And so let's dive into my presentation. Share the window. Okay, let me know if you're able to see my screen right now.
Yep, you can see it.
Okay, perfect. So let's say we're going to start out with a simple example with a spam classifier. So the idea is that we get like an email, and what we want to achieve is for our machine learning model to be able to classify, okay, is this email spam or not spam? And of course, you've pretty much, you've seen like different applications of where this is applied. For example, if you're using Gmail, you definitely have inbox folder, and you also have your spam folder. So how Google is able to handle this is, for example, if you receive an email, it's able to classify, okay, does this email look spamish or is it not? Is it not like not spam? And so let's start for like a simple example. So let's say, imagine that we receive like different type of emails. So we receive normal messages from like our friends. It could be from our friends or families, or it could be from colleagues we work for or work with, along with. And we also receive like some spam. So these are unwanted messages. It could be like advertisement, some like, okay, send me your account, send me your bank details and your PIN, and we're gonna make you rich and other things. And so what we want to do is to like filter out all these spam messages. So let's take for example, so we could start with the idea of like we could make a histogram of like all the words that occurs in a normal messages, which is like we got from friends and families, and we could also make a histogram of all the words that occurred in the spam messages. So I just used these words, for example, like dear friend, lunch, and money. And we could count the amount of times that the word dear appears in our Instagram. Okay. And so we could see, like calculate the probability that the word dear occurs, given that it's a normal message. So it's definitely not spam. So it's like one, two, three, four, five, six. So six out of the total number of word count. So that's like, if you sum all of these up, you get 14, and that's like 0.43. And if you also do the calculated probability that we get a dear message, given that it's spam, so that's like 2 divided by the total number, which is 7. So it's 0.29. So if we also do the same thing for these other words, so we've done the same thing for dear, and we also calculate the probability that we get that the word friend occurs, given that it's from a normal message. So that's 4 divided by 14, 0.02. We also do the same thing for lunch, 3 divided by 4, 0.21, and as well as money. So we have 1 divided by 14. And for the spam, what we could do is also the probability that dear occurred, given that it's from spam, the probability that the word friend occurred, given that it's also from spam, the probability that the word lunch occurs, given that it's from spam, and also the probability that the word money occurred, given that it's from a spam message. And this is all like the calculations. So just to get rid of that, this is how it's going to look like. And so now let's take a simple example. Let's say that we get an email that it says like, dear friend, and we want to check,
Sorry,
okay.
David Price. When you're
Yep.
seeing the presentation, like the intuition behind naive Bayes' first slide currently, when you're seeing that slide only.
Wait, you're only seeing the first slide.
Yeah.
Oh, my bad. What is going on?
Okay,
Wait, what is
now we
it?
see it. Now we see the dear friend naive base slide.
Oh, okay. My bad.
No problem.
Right. Thank you. So, okay, I'm just gonna go through back. So, this is what I talked about, whereby we have like we receive a message that is normal, receive the normal message from friends and family, from family and friends, and we also receive the message like giving like spam, or we also receive the spam message. So these are unwanted messages, and this could be like advertisement. And so what I talked about was like making a histogram. So we have like let's say we make a histogram count of all the words that occurred in the normal message. So yeah, and we could calculate like what's the probability that we got the word dear given it's from a normal message. So we have like 6, 1, 2, 3, 4, 5, 6 divided by the total number of word count, and that's we got like 0.43. And as well we do the same thing for we got the probability that the word is dear given that it's from a spam message, and that's like 2 divided by 7. And what I just did was just to calculate, for example, what's the probability that we got the word friend given that it's from a normal message. So that's 1, 2, 3, 4. 4 divided by the total number word count, so like 418. That's 8. That's sorry, 6, and plus 4, 10, plus 3, plus 1, that's 14. That's how we got that. And we do the exact same thing over here. So what's the probability that got the word lunch given that it's from a normal message? That's 3 divided by 14. And also do the same thing, probability that we got the word money given it's from a normal message. That's 1 divided by 14. And we also do the same thing over here. So for the spam message, so what's the probability that we got the word dear given that it's from a spam message? So that's 2 out of 7. And do the same thing. What's the probability that we got the word friend given that it's from a spam message? That's 1 divided by 7. And we for lunch, it's 0 divided by 7 because there are no recurrent. There are no like this. I made this simple example, so we're gonna see how to tackle this later. And we also calculate what's the probability that we got the word money given that it's from a spam message. That's 4 divided by 7. And so this was the calculation, just the exact calculation without the histogram. And that's like where I start. Sorry about that. I did not know that that part of the presentation wasn't shown. So any questions so far?
All clear.
Oh, okay. Okay. Nice. All right. So now let's take a simple example. Like, let's say we're given the normal message. So the message that we got was, "Dear friend," and we want to classify. Okay, does this word, this sentence, "Dear friend," is it a normal message, or is it like should we classify it as a normal message, or should we classify it as a spam message? And so in order to calculate this, what we just do is we start with our initial probability that okay, what that the probability that it's a normal message. So that's like 6, 0.6. It's basically that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 6 divided by 10. And we also multiply by what's the probability that we got the word dear given that it's from a normal message. So we got the probably what's probably that we got the word dear given that it's from a normal message. That's 0.43 multiplied by the probability that we got the word friend given that it's from a normal message. That's 0.29. And once we do all the multiplication, we get 0.07. And yeah, and we also do the same thing for our we also do the same thing for a spam message. So we start with our initial probability that the word is spam, multiply by the probability that we got the word dear given it's from a spam message, that's 0.29. Multiply that by the probability that we got the word friend given that it's from a spam message, and that is 0.14. And once we multiply that up, we got 0.05. So if we compare the results that we have over here, we could see 0.07 is definitely greater than 0.05. So we could say this word, dear friend over here, is a normal message and it won't be classified as a spam message. So that's just like a general idea behind it. So now you could imagine like we have like a whole like bunch of words. We could have like a paragraph and we'll just do the same thing. So let's say take another example. Like we've seen an example of a normal message. Now let's see an example of a spam message. So we get like the word lunch money money money. So what we're gonna do, we're gonna do the same thing. I'm gonna classify. Okay, is this word lunch money money money? Is it a normal message or is it a spam message? So we're going to start with doing the calculation. So we're going to start with an assumption that the probability that this word over here is a normal message, so that's 0.06, multiplied by the probability that we get the word lunch, given that it's from a normal message. So over here, you could see 0.21, and we could multiply by the probability that we get the word money, given that it's from a normal message. And I did to the power of 3 over here because we have this repeated 3 times. So that's how we got over here, 0.07, excuse me. And once we multiply that up, we get 0.00004. And now we're going to do the same thing with the spam. So we could start out with our assumption that the probability that we get the word that we start out with our initial probability that this word over here is spam, 0.04, multiplied by the probability that we get the word lunch, given that it's a spam message, so that's 0, and the probability that we get the word money, given that we get the word money, given that it's a spam, so to the power of 3, and we get 0. So if you see over here, this is a problem because, for example, this word lunch money money money. Okay, once you see this, we could like, okay, this is definitely like a spam message, and the way that if you even though like our because of this over here, that the probability that we have the word lunch, given that it's from a spam message, because it's 0 over here, no matter what these value over here are, we're always going to get 0. And a way to tackle this is like we could start out with like we could modify our algorithm in such a way that it doesn't start counting from like 0. We could initialize, like for example, this we could like start out like we could add like a number 1 into it. So basically when we have this situation over here, we don't get 0 divided by 7, we get like for example 1 divided by 7. And if we perform this calculation again by adding like ones into each of these histograms, what we get is something different over here. So if you see for this our example, the probability that we got the word lunch, given that it's from a spam message, it's 1 divided by 11, that's 0.09. So now if we perform this calculation again, we could see that the probability that the word, we could see that the probability that this word is spam and times the probability that we get the word lunch, given it's from a spam message, probability times the probability that we get the word money, given that it's from a spam message to the power 3, we could see that the probability is much greater than this in our initial probability that we think that this word over here is a normal message. And so we could properly classify that, okay, this word over here, lunch, money, 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 is definitely a spam message. So any questions? Okay, I guess not. So let's do a bit of some coding. to see how this works. And I'll also talk about like the Gaussian naive Bayes. But I'll prefer like to go through the what my idea is to go through the code with you guys. Then after going through the code, then I'll give you like a like a brief summary with diagrams on how it works. And okay, so let us start coding. I hope you can see my screen.
Yeah, I can see it.
All right. Okay, so we could start out with like importing NumPy and as well as some other libraries, pandas, SPL. No, well, we don't need pandas for this, definitely. And we also need like matplotlib for visualization. So import matplotlib.pyplot as PLT. And also, if I'm going too quick or I'm speaking too quick, you could always tell me to slow down. And we could also add Seaborn, import Seaborn as SNS. And we could also set it, sns.set. Yep. And yeah, we could also add this matplotlib and line. So we don't have to like always keep typing plt.show. So let's start out with, so now what we're gonna do is that we're gonna create like some artificial data set that we'll use for like classification, and we could get this from like from scikit-learn.datasets. Could import make blobs. So basically our data is gonna be drawn from a Gaussian distribution, and we could do something like this: make blobs of how many samples. So n samples. Let's say let's pick very small amount of samples. Could be like 18, and the number of features. We could have like two different features. Centers. We could have like two different centers. Random state. Okay, let's just initialize it to, let's say, 20. That one doesn't really matter. And also cluster standard deviation. We could give it like 1.6, and we could see how it looks like. So now let's make a visualization of it. Basically, okay, just to print this out. Yeah, you can see that over there. And once you, it's also a good idea when you make anything to always check the shape, so you know what you're working with. Okay, so we have like 18 samples and two features over here. And we could also do the same thing for y.shape. Yeah, okay. And continue with our visualization. See how it looks like. Okay, we've got our dots. And now what I'm going to do is that I'm going to set the color. So the color should be based on how our y looks like, based on our target variable, so between 0 and 1. So you don't see it, but we could add something like some color map into it. I think we could have like Federus. I think that's what it's called. Here it is, yeah. Okay, and so now let's start by importing the Gaussian naive Bayes. So from scikit-learn dot naive Bayes, import Gaussian naive Bayes. All right, now, so what we're gonna do is like, we're gonna instantiate our model. So assign it to this variable over here. Okay, once that's done. So something to also tell you about this. So usually you might, and once you're going along in this field, you might hear the word like model and algorithm. And it's good for you to know the difference of of what I mean by what's a model and what's also an algorithm. So before that, let's just fit our data first to this. So now what do I mean by what's an algorithm? An algorithm is basically just this Gaussian model. I think we could see the code. I think probably with a double. All right. So just extend this. So basically, this is the algorithm right over here. This is how it works. So if you're familiar with Python, it's like the init model, and you've got like your fit model, check, and other things. And basically, what it means by a model, this is what a model means. So basically, once you fit your data to the algorithm and the algorithm has learned, then that becomes a model. And now what we could do is like create some test samples so we can draw like a decision boundary, so we could see like how well our algorithm has learned to be able to differentiate between this purple class and this yellow class over here. So we could do something before that. Let's visualize it. Yeah, just create it. Get like X test. So I'll definitely explain what I'm doing over here. Just give me a moment to write it out. I hope this. Could also add some randomness. np.random state, and multiply by, let's say, 500 samples and two features. And we could do is create a y predict and model.predict. So basically what I did over here was just generated a couple of new samples, and we use a predict statement to see how our algorithm basically just like, okay, since I've given you this data, so basically this X and Y, you've learned from it. Now I'm going to give you like a data that you've never seen before, and I want you to predict, okay, does this belong to the class 0 or class 1 over here? So once we run that, and we could make the plot of it. So plt.scatterplot x test and x test again. So the first feature, second feature, and the color should be based on my y predict. Okay, and we could make it a bit much visible. And CMap RU BU. Let's say ready B. There we go. So we could reduce the alpha level. Say make it a bit brighter. Cool. Now what we're gonna do is we're gonna plot our original samples that we got. So basically what we use to train the model. So let's say it's X of 0 and X over here of 1. An idea of how it looks like. So we've got our dots. Okay, so we need to modify this. So over here it means like the first one over here means like our X coordinate, X1 and X2, and this is Y1 and Y2. So basically X1 over here, it's my starting position. So let's say I wanted to start from -1 and go all the way to 10. So we have like -1 over here plus that. So that's 11 from the -1 all the way to 10. So 11. And for my y-axis, I want it to start from -15 and go all the way up to, oh wait, before that, we could draw the color to get a good idea of what's going on. And put a C map, a color map, RDBU. Okay, so it's all the way up there. So I wanted to start from -1 all the way to 10. And for the y-axis, I wanted to start from 0 and go all the way to, let's say, 11. And we could draw that. Okay, I could make this alpha level a bit like this. So if you can see my screen, you could see the decision boundary that what our model drew over here. So basically, if we get a dot over here, what we do is that we're going to classify it as the red class. And if we get a dot that is over here, it's going to be classified as a blue class. So is that clear? All right, I guess so. So now what we could do is that since we've been dealing with probabilities, like from this presentation, we've seen like we're calculating probabilities. We also have like this function that also returns the probabilities. So I could do something like this, y probability and model dot predict. So we have got log prob and also predict the probability of what x tests. And once we run that, okay, that's quite a lot. So we could just limit it. So let's say the first 10, 10 rows and all the features. So we get these values and we could round them to like 2 decimal place. So over here, what we could see is like, okay, so for, let's say for basically these are ours. This is just like a sample. Let's say we picked like 10 and let's say 9 over here. And oh, we could basically, well, we could actually visualize the dots to could see them properly. Let's reduce it to 3, the first 3 samples with all the columns. So if you look at this, I could bring it all the way up here. So if we have like on our x coordinate 5, so that's like right over here. And on our y coordinate, we have something like 7, which is like somewhere around here. We could see that it's definitely more towards this class than towards this other class over here. But before that, what to be sure, yeah, that's it. Yeah. And if you also take like the second one over here, so we have like 5 and 5. So it's somewhere around here, 5 by 5. So it's more towards the blue class than towards the red class. And we could try this one over here. So we have 3.66, so it's like somewhere around here. And on our y-axis, we have 7. So you could see that it's more towards this red class than towards this blue class over here. So is that clear? All right, I guess so. So now let's work with something like, let's work with a data set that we're pretty much familiar with. So with the iris data set, so it's a flower data set. So we could load it from scikit-learn from data set, import load iris. And what we could do is that we store it to this variable over here. Now we could create our, so assign our data to the X value over here. So these are our features, and Y data.target. These are our labels. So if we print this out, so just to get an idea, data dot feature names, we have like the sepal length in centimeters, sepal width, petal length, and petal width. And if you take a sneak peek of like our feature matrix, okay, not, it doesn't have head, do we call it? Let's see what it looks like. Okay, all right. So let's get the first 5 samples. 0. So basically over here, the first one, 5.1 is our sepal length, 3.5 it's our sepal width, and 1.4 is our petal length, and 0.2 is our petal width. I want you to memorize this just to give it clear. So when I'm explaining the how this Gaussian naive Bayes work, you understand it properly. So now let's import like a function that helps us to split our data sets into like training and test sets. So some scikit-learn dot model underscore selection, import train, test, and split. So now what we could do is like x train, x test, y train, and y test. If you're wondering how this all came about, if you just call this function over here, this is how it's supposed to be done. That's how you're gonna do it over there. So if you're not familiar with this, the idea is like, so I'm just gonna open a simple canvas and draw something. Okay, you've got that clear. You're drawing. So the idea is like, let's say we have like our data over here, and we've got like our sepal length, sepal width, sepal length, width, petal length, and petal width. And we want to take like, let's say we want to use like about 80% of our data. So like this is the top over here. We want to give this a model. Okay, model, take this part of our data set and learn with it. And later on, what we're going to do is like the remaining 20%, we're going to use it to test the accuracy of our model to see how well it performed when we give it like some unknown set of data points. So basically, it has already known like these set of features over here. So we're going to give it new features to see how well it performs when making predictions. Okay, so we're going to pass x and y, and the test size is 0.2. Okay, we could also check the shapes. And shapes of x test dot shape, print y train dot shape, and finally y test dot shape. So you could see over here for our x test, if you calculate this, is in total we have 150 samples. So if we take 20% for testing, that's like 30 samples over here with 4 features. And for trading, if we took 80%, that's like 120 samples. And so what we could do right now is to feed this into our Gaussian naive Bayes model. So call in the model parameter, Gaussian NB. So model.fit. So this is where, and what we're going to give it now is this part of our data sets. Like if you see what I mentioned here, this 80% for the train. So what I meant by 80%, these are like, for example, the features. And we're not only giving it the features, we're also giving it the labels corresponding to these features. So let's say we got like Let me just print this out. So for X train, oh, let's say we get like the first sample with all the features. So basically, this is the sepal, to be sure, sepal length, sepal width, petal length, and petal width. These are all this numbers. And if we check the labels corresponding to this feature, which is 0, it belongs to class 2. And to also mention that, like, what does class 2 actually mean? So if we check data dot target names, we have three different type of flowers: Sethosa, versicolor, and virginica. So class 2 is should be definitely, if we split it correctly, but okay, let's, to be sure of this, let's say we get the first and all the features. Basically, what this over here when printing is because before we started splitting. So over here, this is actually how it is now. Yeah, this is correct. So for this set of features over here, it corresponds to this label 0. And what does 0 actually mean? It's this Sethosa. And if we have something like, let's say we take something like, should be like 99 and 99 over here, we print them out. It's definitely belong to class 1, which is this one, versicolor. And also 140 over here. It definitely belongs to the third class, which is virginica. Okay, so to get the idea of that, so now we're gonna pass this. So now this is when the model is learning, it's done learning. And once it's done learning, what we're gonna do now is to make some predictions on, so now is the part where I talked about we've given it 80% of our features and as well as the target labels. So now we're gonna give it like 20% of our remaining features. So this is, it's basically this part over here. But we're not gonna give it this target labels over here. We're only gonna give it this set of features over here. And once the model makes predictions of like what these labels are with respect to the feature that was given to it, what we're gonna do is that we're gonna compare what our actual labels with what the model actually predicted. And so we're gonna do that. Y predict is equals to, let's say Y predict of Iris. We have something similar to that. So we could use the predict probability of X tests, and we could print this out. You get these numbers. And the reason why you get these numbers, just to round it into 2 decimal places. So now you could see, remember that we have like 3 target variables, target names. So this one over here, Sethosa, versicolor, and virginica. So basically for this first feature over here, so the first one with all the labels, for this feature over here, so 6.1, 2.8, 4, and 1.3, it predicted that, okay, this definitely belongs to class 1, which is versicolor over here. So we do the same thing for, like, let's say if we have like 13, and for this feature that we gave it, so that's like 1, 2, I could just get it here, 13. So basically it predicted that, okay, it's still the same one over here. And so what we could do now is to actually compare basically what our model predicted with our actual values. So we could do this. We could do this in this way: model.predict. So we don't get those probabilities. X test. And we could see y predict. So we get something like this. It's basically what you've seen, but this, we're not showing the probabilities. We're just only showing like the actual ones, the actual, the basically the target names, but presenting them in 0, 1s, and 2s. And over here, we have like our Y test. You could see over there. And once we compare this with our Y test, get some booleans, we could sum that up. 30 divided by the total length of samples. It's like X test. And we get like definitely 1. So we get like a 100% accuracy. So it basically, what does mean that our model actually performed very well on a set of data set that it has never, on these 30 samples that we gave it. So we could also play around. Let's say, let's give it like, let's only use 40%. I mean, you definitely don't want to do this in real life, but just to see, play around with it a bit. So let's say, let's give it like 40% for training. So basically the idea is that we're no longer giving it something like this. Let's get a new layer. Okay, that doesn't work well. Okay, not familiar with this tool. Let's draw a new image. So the idea is that we're no longer giving it 80%, but now we want to give it like 40%, this part, corresponding to the label. So we want to give it this part for training, and we're going to use like 60% for testing. And let's see how it works with this. So you could see like the samples reducing. Train the model and make some predictions. And you can see like the accuracy is like 93%. So you could also keep playing around with this and you could see how well it works. On a normal case in practice, you pretty much either want to use like, for example, 80% for training or 20% for testing, or 70% for training and 30% for testing. Any questions? All right, so basically I'm just gonna revert everything back to what we've done so far. Like use 20% for testing. So yeah, see in this case it's like 90%. Now what we could do is that we could draw like a confusion matrix. So we could see like basically how was there like some, in some cases that our model was a bit confused on some set of data points, whether it belonged to either class 0, 1, or 2. And we could do this by this way. So basically we could import our confusion matrix. So from sklearn.metrics, import confusion matrix. And we have mat confusion matrix. So we begin to pass the true, and the predicted is our y predict is, and we could draw like a heat map using from Seaborn heat map over here, matrix transpose. We could start doing some configurations. Let's say add some annotations. Annotations, true. Okay, and we could also keep working on the color. This. Okay, it's getting better and better. You could specify the format, decimals, square. So it looks rectangle, could make it squarish. What else could we do also? Oh yeah, could also label the X ticks. I see. Labels should be our data.target names. So those are those 3 different classes, and same thing for our y tick labels. data dot target names over here. So basically, yeah, we could also do something else again. Yes, I think that's it. Yeah, we could also add, yeah, of course, our labels, plt dot. So for our y label over there, we could put like our, this should be predicted, and plt dot x label, the true ones. Okay, so if we see over here, basically we've got like, for example, for Sethosa, we've got like what our meta predicted 8 out of that. So for versicolor, we could see like the confusion over here between these two different classes over here. So that's why, of course, you could see the accuracy wasn't correct because there were some misclassifications over here. And over here for Virginica, there was no misclassification over here. But over here, for this versicolor, there was some misclassification between versicolor and Virginica. And so pretty much that's for that. And yeah, so that. Okay, so I also promised you guys a visualization to a brief understanding of how, like, for example, for example, how the Gaussian naives work. So I could present my screen again. I think I have some issues with sharing again. What's that? Okay, I should be able to share now. Okay, so let's see, I've got my board over here. So basically, if we saw that we had like those three different classes, like just to refresh. So Sethosa. So I'm just going to use like some abbreviations, S for that. Versicolor, so V, C, and for Virginica, VG. And so if you remember behind what we've done over here, so let's say we've got like, basically where I'm going to draw something like this. And basically with respect to these features over here, let's say we have like the sepal length and the sepal width. So I'm just going to use these two examples, but we can also generalize it to these other two over here. So for this one over here, if we draw for our sepal length related to the, okay, so basically I think it's much better if I use different colors over here. So we've got like S, and we've got like the VS, should be much better, and Virginica, VI. So if we make a plot, so for example, for this feature, sepal length, go write it over here, sepal length. We've got something like this. So for this one over here, so we could draw like a Gaussian distribution, something like this. For VS, versicolor, we draw something like this. And for VI, let's say we could draw something like this also. And for this part, for the Gaussian naive Bayes, what we're calculating, we're not calculating probabilities, but we're calculating likelihoods. So basically likelihoods are things that already occurred, and probabilities are, for example, things that like about to happen in the future. So for like a likelihood, so for example, this part over here, this is like 5.1. This because of that's all these features, take them into account. So we also have like 4 point. So let's take this, for example, this one over here, 1.5. So let's say if we have something like this, we got put this a bit down. We got 0, 3, and 5 over here. So if we draw the likelihood, so it should be somewhere around here. That's it. And we're also going to do the same thing for our sepal length. Oh, no, 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 no. Go back. And go away. Okay. And now I'm just going to put this in a new page. So now this one will be our sepal length. Wait. Previous page. Sepal length. Oh yeah, then we have sepal width over here. Okay, and we also do the same thing. So we've got like 3.5. So that's like, okay, this line is not supposed to be here. Just remove it. And that's like 3.5. So it's like somewhere around here. Could say, for example, with the red color. Draw the likelihood. So now what we want to do is like, we want to see, okay, does this flower here, based on all these features, so basically the same thing that I've done for sepal width length in the previous page, and sepal width, we're also going to do the same thing for petal length and petal width, draw the same diagram, and with plotting these likelihoods over here. So we have like 1 and 0.2 over there. And what we're going to do is like, we're going to calculate what's the probability that it's from this class, and also from this class. So if you remember behind this, when we're working with the spam classifier, we start out with our initial calculation that there was a probability that it's a normal message or spam message. So in our case, it's going to be what's the probability that it's actually from this flower, Setosa, versicolor, and Virginica. So, and in this data set, the way it is like, we have like in total, we have like 50 samples. And for these three colors, they're like 150 samples actually. And for this actually flower, we have 50 samples assigned to it. Another 50 also assigned to this, another 50 also assigned to this. So you could start out like with sample, let's say the probability that it's actually Setosa, given the petal, given the sepal length 5.1. Wait, the probability that it's a sepal. Wait, just go back to my presentation. And dear friend, given this, so we've got like 5.1, given that it's from this class, Setosa. I'll just use the abbreviation S. And we also multiplied by the oh yeah, so actually, sorry, first we should start with this. Right, oh, why can I get the whole thing? There we go. Okay, the probability that it's from this class, Setosa, right over there, times the probability that the sepal length is 5.1, given that it's from this class, and also do the same thing that we got what's the probability that it's 3, that our sepal width is 3.5, given that it's from this class also, times the probability that our sepal width is, so I'll just use, sepal width is 3.1, given that is from this class, C theta. And oh, actually, and I actually made a mistake over here. So since I mentioned that we're not dealing with probabilities over here, we're dealing with likelihoods. So what's the likelihood that our sepal length is 5.1 given that it's from Setosa? The likelihood that it's 3.1 given that it's from the Setosa class. And once we do all the calculation, so we get like for example, let's say 0.3 over there, and we could multiply it by this one over here, multiply it by this probability over there. So I mean, we just need to do all the calculations, and once we add them up, basically once we add them up, we get like a value. Let's say we get like a value over there. And we also have to do the same thing for these other classes. So for these other classes over here. So what's the probability that it's not going to be S, but it's going to be vesicolor, given we start out with our probability that it's a vesicolor multiplied by the likelihood that it's 5.1, given it's from vesicolor, V over there, VC. And we also do the same thing, the probability that it's virginica multiplied by the likelihood that it's 5.1, given that it's from this class, times the likelihood that it's 3.1, given that it's from this class also. And once we like do all the calculations, and let's say, for example, for this, in this case, for C theta, I'm just going to make it like a random example. Let's say we get like 20. And for vesicolor, we get like 30. And for virginica, we get like 40. So basically, this value over here is definitely higher than these other ones. So basically, we're going to assign it to this class over here, virginica. And that's how the idea works. It's basically similar to this. And also over here, it's also good to notice that sometimes this value over here, it could be really, really small. Like if we've seen in some other cases over here, I remember the exact example. We could get like some really, really small numbers, you know, it could be like 0.000 something over here. And what it's preferable to do is to take the log of these numbers, make a new page, put that over there. So I'm just going to rewrite it again here. So after performing all that, you just take the log of the probability that it's from this class, Sitosa, times the likelihood that it's 5.1, given that it's from this class, Sitosa, times also the likelihood that it's 3.5, given that it's from Sitosa. And you also keep doing the same thing, the likelihood times the likelihood that it's 1.4, given that's from this class, times 0.2, given that's from this class. And once you take the log of like everything inside there, you get something like this. The log of P of S, and this time to come plus the log of 5.1, given that it's from Sitosa, plus the log, wait, there's a mistake over here. Yeah, the log, likelihood, yeah, 5.1, given that from S. And we just keep on doing the same thing for the other features. So that's like a general idea. So if you're able to understand like how these naive Bayes works, the Gaussian naive Bayes, it's very, very simple. And you also have more like the multinomial naive Bayes. And I also recommend you to check that out. And I left some links over here in the script I gave to you guys for you guys to also further dive deep into it. So basically, just a quick summary of all these models. So this model, they are extremely fast for both like training and making predictions. They also provide some straightforward probabilistic predictions. So basically, what we've seen over here, which gives us a good idea, was there. So it could like 0.72 and 0.28, and we could see that they're only like they have very few like tunable parameters than if you compare them to other models like SVM, and also it's high bias and low variance because it usually works well in practice. And any questions? Okay, I guess. Well, thank you very much for listening.
Thanks, David Price. Enjoy your
Yeah,
weekend.
you're welcome. And you too.
All right. Cheers, everyone.